Welcome back to the deep dive. Today we are strapping in to examine a true industrial behemoth, the next generation hybrid cement mixer truck.
And we're not just kicking the tires. We have the engineering blueprint for its heart, the electric drum drive system, or EDDS.
Exactly. Our mission today is to really extract the core technical innovations from these functional specifications. This is a huge strategic pivot.
It really is. We're looking at the fusion of, demanding industrial robustness with the highest standards of automotive functional safety, specifically ISO 262622 ACLC.
And that's the crux of it. This isn't just swapping out a motor. It's about moving from old, incredibly inefficient hydraulics to precise 400-volt electrification.
And it's all about solving problems that have plagued fleet managers for decades. The sources we're looking at, these are detailed engineering reports, and they make it very clear.
This isn't just to meet emission standards. The goal is to slash the total cost of ownership, the TCO, by radically improving efficiency and, believe it or not, the concrete quality itself.
Exactly. And to set that strategic context, you really have to understand the two major historical limitations of the old systems.
Okay, let's start with the big one, the energy waste.
It's just terrible. Think about that conversion chain. You've got the engine running, powering a PTO, which drives a pump, pushing fluid through hoses, and then finally, a hydraulic motor turns the drum.
So many points of failure and so many points of loss.
At every single stage, the total system efficiency often hovers between, 40 and 50%?
Wait, 50%? So half the fuel you're burning just to mix the concrete is literally just wasted as heat.
Gone. Just radiated out into the atmosphere. Over a truck's 15-year life, that is a staggering amount of wasted money and fuel.
Okay, that's a huge drain.
Yeah.
But you said there was a second issue, something that affects the final product.
Yes, and this is arguably even more critical. It's what engineers call the strong coupling problem.
Meaning the drum speed is tied directly to the engine speed.
Exactly. So picture a driver stuck in stop-and-go traffic. To save fuel, the engine idles low. But because of that coupling, the drum speed also slows way down.
And that's bad for the mix.
It's terrible. It compromises the consistency, the homogeneity of the concrete. And remember, concrete is a perishable product with really strict quality standards.
And the reverse is also true, right? If the driver is worried about the mix, maybe they have a high-quality requirement they have to. Kind of just rev the engine higher.
That's the only option they have. They have to force the engine to run at a higher, less fuel-efficient RPM just to keep the drum spinning fast enough. It's this constant, awful compromise.
You're trading fuel economy for product quality, or vice versa. You can't win.
You can't. And this new electric drum drive system, the EDDS, it solves that completely. The engineering blueprint lays out 4 core goals.
Okay, what are they?
First, complete speed decoupling from the engine. Second, extremely high efficiency. Third, energy recovery through regeneration.
Then the fourth has to be safety.
Underpinning it all, yes, ISO 26262 ACLC compliance. They are designing a system for high performance and, just as importantly, absolute resilience.
All right, so let's unpack that strategic shift. We talked about that 40–50% efficiency. How much better is the electric route, really?
Oh, it's a night and day difference. With the old hydraulic system, the losses just pile up. Friction in the pumps, throttling in the valves, viscosity effects. It's a mess.
But the electric path is much simpler.
So much simpler. It's just high voltage battery to the motor control unit or MCU, to the motor, to the gearbox, that's it. The chain is shorter and every link is vastly more efficient.
So what's the new number? What efficiency are we talking about?
You're jumping immediately to maybe 85, even 90% system efficiency in its optimal range.
Wow.
Now think about that from a TCO analysis. You're basically doubling your efficiency for the 30,000 hours this truck is operating. The savings they're transformative. That's the business case.
So let's go back to that decoupling. What's the biggest single operational win from separating the drum from the engine?
It's achieving what we call constant speed drive, or CSD. This is mainly for the agitating mode, which is when the truck is just driving from the plant to the site.
Right.
The EDDS can lock the drum speed at, say, a very precise 1 to 2 RPM. This slow, constant churn is absolutely paramount for maintaining concrete homogeneity.
And it doesn't matter what the vehicle's doing.
Doesn't matter at all. The chassis engine could be idling, it could be at highway speed, it could even be temporarily off in a hybrid stop-start cycle. The drum just keeps doing its job perfectly.
Which puts the concrete quality first, not the engine's needs. I love that. Now, regeneration. Regen in a cement mixer sounds counterintuitive.
But think about the physics. You have a massive, heavy drum acting like a flywheel. A fully loaded mixer can have 12 cubic meters of concrete in it. That's nearly 29 metric tons.
Okay, so that's a huge amount of inertia.
A huge amount of kinetic energy, and when the operator slows the drum down from charging speed or during the entire unloading process, all that energy has to go somewhere.
In the old system, it was just heat, wasted.
Pure waste. The hydraulics would just get hot. Now, the electric motor flips its role and acts as a generator.
And it sends that power back to the battery.
Channels it right back into the 400-volt high-voltage pack. For a heavy commercial vehicle, every single kilowatt hour you can capture is a massive gain. The drum goes from being a pure energy consumer to, at times, an energy contributor.
Okay, before we dive into the guts of the hardware, let's just define the boundaries here. What are the core components the engineering team is actually responsible for designing?
The source material is very specific about this, which is good practice. The scope includes 4 main things: the permanent magnet synchronous motor, the PMSM, the motor control unit, which is the inverter, then the dedicated reduction gearbox, and finally the thermal management assembly, which is the liquid cooling system for the motor and the controller.
Got it. And how does it talk to the rest of the truck? How does it know what to do?
It uses the standard commercial vehicle architecture. The hybrid control unit, or HCU, is the master controller.
Okay, so the HCU is the brain.
It's the brain. It sends high-level commands like agitate mode or target speed 14 RPM over the standard CAN bus, which for these trucks is SAE J1939. The MCU for the drum is the slave. It just executes those commands.
But it must have to talk to the battery system too, right?
Yeah.
Especially with regen.
Oh, crucially, yes. It has a constant dialogue with the battery management system, the BMS. The BMS tells it 2 critical things. First, is high voltage even available?
And second,
even more important, what is the allowed charging current right now? If the battery is almost full, or maybe it's too hot, the BMS will say, hey, you can only send me 50 amps of regen.
And the MCU has to obey that instantly to avoid damaging the battery.
Instantly. Defining that clear master-slave relationship and those interfaces, I mean, that's the absolute foundation for getting a system like this to work.
Okay, so we've established the why. Now let's get to the where. We're moving from the strategy to the battlefield, the construction site. Section 2. Engineering for the extreme.
This is where the specifications really separate a standard automotive part from a truly heavy-duty industrial one. The demands are just extreme.
Let's start with temperature.
The system has to operate continuously from minus 40 degrees Celsius.
Wow, that's deep winter in Canada territory.
All the way up to a blistering plus 85 degrees Celsius.
That's a massive range. And that kind of swing can cause materials to fatigue and crack over time.
Absolutely. And the cooling spec is just as tough. It has to deliver full rated power as long as the coolant is below 65 degrees Celsius.
So deaerating, cutting back performance to protect the hardware, that's only allowed if it gets hotter than that.
Right. Which means on a hot summer day, the truck can still perform at its peak. If it starts limiting performance just because it's hot out, it fails the operational spec. That's a non-starter for fleet owners.
Okay, now let's talk about the real enemy here, the cement slurry itself. It's abrasive, it's sticky, and it's incredibly corrosive. How do you protect against that?
The ingress protection, or IP ratings, are extremely stringent. The main electronics box, the MCU, has to be IP67.
So dust-tight and can survive being temporarily dunked in water.
Yes. But here's the really demanding part. The connectors, where the wires plug in, they have to meet IP6K9K.
IP6K9K. That's a very specific rating. What does it mean?
It's specifically for protection against close-range, high-pressure, high-temperature water jets.
So pressure washing.
Exactly. You have to assume that every single day, the operator is going to blast these components with a pressure washer to get the concrete off.
And if they don't, that slurry hardens and just encases everything.
Right. And it's not just water. The source highlights this. Cement slurry is highly alkaline. We're talking a pH of over 12.
Which is incredibly caustic.
It's a chemical attack. So all the materials, the metal coatings, the rubber seals on those connectors, they have to be designed to withstand a high-pressure chemical jet day in and day out for 15 years.
So it's not just a mechanical challenge, it's a material science challenge. Now, beyond the chemical attack, there's the mechanical stress. The
Yeah.
The sloshing.
This is maybe the toughest one. You've got nearly 30 tons of a semi-liquid mass sloshing around inside a rotating cylinder.
The forces must be immense.
They're huge and they're complex. The spec says the system must meet SAE J1455 heavy-duty truck standards, and that includes surviving 5.9 Gs of random vibration.
5.9 Gs. Let's put that in perspective.
It's far beyond what most passenger car components would ever see. It's just relentless, low-frequency, high-amplitude shaking. That sloshing puts incredible torsional loads on the motor shaft, the mounts, the gearbox.
If you don't design for that specific vibration signature, things will just fatigue and break.
And quickly. And then the final mandate is just brutal. The operational life.
What are we talking about?
The design life is mandated at 30,000 hours or 15 years.
30,000. A typical automotive part might be, what, 5, maybe 10,000 hours?
Exactly. You're tripling the life expectancy. That requires huge design safety factors, premium materials, and just obsessive thermal management.
The takeaway here really is that every single decision, from the choice of seals to the cooling system, it's all driven by ensuring uptime over a 15-year life in a hostile environment.
Absolutely. Because if the system fails at 10,000 hours, that efficiency gain we talked about is totally irrelevant. The replacement cost just destroys the TCO. In this world, durability is profitability.
Okay, let's move into the heart of the system then. Section 3, the core power unit. The spec calls for an IPM-PMSM, interior permanent magnet synchronous motor. Why that specific type?
The choice really comes down to two critical moments in the mixer's daily life. The first is what engineers call the breakout condition.
Tell me about breakout.
Okay, so concrete is thixotropic, which means if it sits still, even for just a few minutes, it starts to settle, and its internal resistance, its yield stress, goes way up.
So it gets harder to move. I've heard stories of older trucks just stalling their engines trying to get a settled drum moving again.
It's a huge problem, and this is where the PMSM is superior. Its permanent magnets give it incredible torque density at 0 or very low speed. It can deliver a massive, instantaneous kick.
Unlike a standard AC induction motor.
Right. An induction motor needs a moment for its magnetic field to build up. It's just not as good at providing that immediate explosive torque you need to break that settled mass loose.
So it solves a major operational headache. What's the second justification?
It's about efficiency during that long agitating mode we talked about. The truck spends most of its life just slowly turning the drum at low torque.
Right.
A PMSM is incredibly efficient at part load. It doesn't need to waste current just to magnetize the rotor like an induction motor does, so it can maintain that 90+% efficiency even when it's just ticking over. That's the TCO winner right there.
Let's talk numbers. For a big 10 or 12 cubic meter truck, what kind of power are we looking at?
The continuous power, what they call S1 rated, is 60 kilowatts, but the peak power for 60-second bursts has to be 100 to 125 kilowatts.
That's a huge peak. And the torque.
The peak torque at the motor shaft needs to be massive. The spec calls for between 850 and 1,200 newton meters.
And you need that because of the gearing.
Exactly. This motor is paired with a huge reduction gearbox, something over 200 to 1. That peak motor torque gets multiplied into an enormous force at the drum, which you need not just for breakout, but for starting a full load while the truck is climbing a steep hill.
Okay, let's talk about a crucial detail here. The sensor choice. The spec is totally inflexible on this. It demands a resolver. Why this older analog technology instead of a modern digital encoder?
This goes right back to the durability requirements we just hammered home. A resolver is fundamentally rugged.
What is it exactly?
It's basically a rotary transformer. It's just copper coils and an iron core. There are no sensitive electronics inside it. It's built like a tank.
So it's resistant to all the things that would kill a normal sensor.
Vibration, high temperatures, oil, dust. It just shrugs it all off. A modern optical encoder with its fine glass disc and sensitive optics would fail very quickly in that environment.
So you're trading a tiny bit of precision for a massive gain in reliability.
And when you're talking about an ASIL-C system, reliability is everything, which leads to the other requirement for the resolver, redundancy.
For the safety case.
Yes. For ASIL-C, you need to be able to verify the motor's position. So the spec demands a dual-channel reading from the resolver, 2 independent signal paths.
So if one channel gives a crazy reading, the other one can confirm the motor's actual state.
Exactly. A single sensor failure can't be allowed to cause a hazardous event.
Okay, let's shift to the brains of the system, the motor control unit, the MCU. What are the key specs for the inverter?
Well, it's running on that 400-volt platform, so it takes in 250 to 480 volts DC. It has to deliver about 250 amps continuously to the motor, with peaks up to 400 amps.
And the sources mentioned a big decision point here, the type of transistors to use.
Right, the classic trade-off. Standard IGBTs versus the newer silicon carbide or SiC MOSFETs.
What's the argument for 6 here? It's more expensive, right?
It is more expensive, but SiC has much lower switching losses than IGBTs. For this truck, that efficiency gain is most pronounced in that low-power agitating mode.
Where the truck spends 80% of its time.
Exactly. So while SiC adds to the initial cost, the return on investment over 15 years from those sustained efficiency gains, it justifies the higher price. It lowers the TCO.
Let's talk about the critical hardware safety features. The last lines of defense. The high voltage interlock, or HVIL.
This is non-negotiable. It's a simple, low-voltage safety circuit that runs through all the high-voltage connectors.
And the key is how it disconnects.
Yes. The HVIL pins are designed to be shorter. So when a technician starts to pull a connector apart, the HVIL breaks contact first.
Which instantly triggers a shutdown.
Instantly. It tells the MCU and the BMS to open the main contactors, killing the 400-volt power completely before the main power pins separate.
So it prevents a deadly 400-volt arc.
A huge electrical flash, yes. It's a fundamental safety mechanism. And alongside that, you have the hardwired emergency stop input.
This is the big red button.
It's the big red button, and it has to be completely independent of all the software and the CN bus. When that button is pushed, the MCU must execute safe torque off, or STO, and cut power to the motor no matter what any other system is telling it to do. It's the ultimate physical override.
This moves us perfectly into Section 4, the intelligence. This is where the raw power meets the sophisticated control algorithms.
Right, because this is about so much more than just turning a motor on and off. You're managing the complex physics of a fluid load. Let's look at the 3 core operating modes.
Let's start with charging mode. That's high-speed reverse to load the concrete.
Right, 12 to 16 RPM. But the control logic can't just command a speed. It needs an initial torque boost.
Right.
To overcome the initial static weight and friction of that first batch of wet material hitting the drum. Without a calibrated boost, the motor could lag or even stall for a second, which makes loading inefficient.
Okay, next is agitating mode, the long-haul transport phase.
This is the efficiency sweet spot. You're using that constant speed drive to lock the drum at 1 to 2 RPM. And because the load is low and constant, the MCU runs an algorithm called maximum torque per ampere, or MTPA.
MTPA. How would you explain that in simple terms?
Think of it as the motor being hyper-efficient. The MCU is constantly adjusting the magnetic fields inside the motor to make sure that for the tiny bit of torque it needs, it's drawing the absolute minimum possible current from the battery.
So it's all about maximizing battery life during that long drive.
Precisely, keeping the system well above 90% efficiency. Then finally, you have discharging mode. This is all about precision.
Right, the operator is carefully placing the concrete.
So you need stepless, perfectly smooth speed control from 0 up to maybe 14 RPM. Any jerkiness or hesitation can lead to waste and quality problems. And of course, this is where regen is most active, capturing energy every time the operator slows the drum.
Now for the really advanced feature, active damping. Sloshing suppression. What's a core problem with the concrete sloshing around?
Well, it's a few things. First, it affects vehicle stability, which is a safety issue. Second, the constant torque ripple from the slosh puts a lot of stress on the gearbox and motor, causing wear.
So how does the motor act as a shock absorber?
It's an intelligent cancellation process. The MCU is constantly monitoring for tiny fluctuations in motor speed and torque. It uses an internal mathematical model, an observer, to estimate the exact frequency of the slosh.
Okay.
And once it knows the signature of that unwanted oscillation, it injects a perfectly timed anti-phase torque signal back into the motor.
Ah, so it's like noise-canceling headphones.
That is the perfect analogy. The sloshing is the noise, and the MCU is playing the opposite sound wave of torque to cancel it out in real time. It's actively fighting the physics.
That's brilliant. Now we have to talk about the biggest commercial risk. The Manguan risk, concrete hardening inside the drum.
It's a total financial catastrophe. If that happens, the truck is often a write-off. The system has to have a robust emergency strategy for this.
So what happens if the main high-voltage system fails?
First, the MCU must immediately command safe torque off. It cuts power to the motor and then puts it into a freewheel state.
So there's no electrical resistance from the motor locking up the drum.
Exactly. But the concrete is still in there, and the clock is ticking. So the spec mandates a physical failsafe, the mechanical emergency drive interface.
An access point on the gearbox or motor?
Yes, a dedicated port where a crew can connect an external power source, like a portable hydraulic unit, to physically turn the drum and get the concrete out before it sets. It's the ultimate last resort.
Okay, let's wrap this section with the diagnostics. The system uses a 3-level fault hierarchy.
Right. Level 1 is a symbol warning, something minor. The system logs the fault, maybe limits torque a bit, but keeps running.
Level 2 is a derate or limp home mode.
Correct. A more serious but non-critical fault, like the system getting a little warm, it will restrict performance, maybe lock the drum at 2 RPM, but it allows the driver to get back to base safely.
And level 3 is the critical shutdown.
This is for anything that threatens safety or integrity. An overcurrent, an HVIL disconnect. The response is immediate safe torque off. The truck is dead in the water until it's fixed.
That systematic approach leads us right into the final engineering pillar. Section 5, the ISO 26262 ACE-LC architecture.
And this is all about the process of design. Achieving ACE-LC requires incredible rigor, starting with a hazard analysis and risk assessment, the HAO.
Right, where you rate everything on severity, exposure, and controllability, S, E, and C.
Exactly. Severity S3 is catastrophic, loss of life. Exposure E3 is high probability, and controllability C3 means the average driver has no chance to prevent the harm.
And the ACRA identified 2 hazards that reached the ACE-LC level. What was the first one?
Unintended reverse rotation while driving. Imagine the truck is on the highway and the drum suddenly switches to high-speed discharge.
Concrete flying everywhere. It would be a disaster.
A multi-car pileup, so that's S3 for severity, E3 for exposure, and C2 for controllability. That combination gets you to ACE-LC.
And the second one?
Uncontrolled overspeed during unloading. The drum spins way past its limit, flinging concrete or water violently. That's also S3, but E2 for exposure and C1 for controllability, which also lands it at ACE-LC.
And so the safety goals are just direct countermeasures to prevent those things from ever happening.
Precisely. And the rest of the process is proving you've met those goals with layers of defense. We have the hardware safety mechanisms.
Like the HVIL we talked about, and the safe torque off circuit.
Right. And the active discharge circuit, which is a really important service safety feature. It dumps the high voltage on the DC bus to below 60 volts within 5 seconds of a shutdown.
So it's safe for a technician to work on. And the redundant sensors, of course.
The dual-channel resolver and redundant current sensors are mandatory hardware defenses.
Then you have the software safety mechanisms on top of that.
Yes. This is the dynamic safety management. The software runs a safety state machine, and it performs constant rationality checks on all commands.
So rationality check.
For example, if the main controller commands charge mode, but the vehicle speed sensor says the truck is doing 60 kilometers an hour, the MCU software has to say, that's not rational, reject the command, and enter a safe state. It's a skeptical gatekeeper.
And the core of ISO 26262 is making sure all this is connected. Traceability.
It's the paper trail that proves you did everything right. Every safety goal, like prevent overspeed, has to be traced to a specific functional safety requirement.
Which is then implemented by a specific hardware or software mechanism.
And every one of those mechanisms has to be verified by a specific test case. This full chain traceability, often managed in a systems engineering tool like SysML, is the absolute proof that your system meets the standard.
That rigor is incredible. Which brings us to our final section, the validation strategy. How do you prove this design is ready for 30,000 hours of punishment?
It's an exhaustive multi-stage process. Stage 1 is the bench test in the lab.
What are you testing there?
First, you confirm the efficiency map. You have to prove that the 90+% efficiency zone covers the entire agitating mode range. Then you do a thermal rise test. Run it at full power for 8 hours straight to make sure the cooling system holds up.
And the most aggressive test.
The locked rotor test. You physically lock the motor shaft and then command peak current for 30 seconds straight. It's simulating the absolute worst-case breakout condition to verify the thermal limits of everything.
Wow. Okay, stage 2 is environmental testing.
This is accelerated aging. You have the thermal shock test, 500 cycles from -40 to +85 Celsius in under 10 seconds.
That's designed to break anything weak.
Any weak solder joint, any bad seal. Then you have the 720-hour salt spray test to validate corrosion resistance. And of course, the big one, the random vibration test, 5.9 Gs on all 3 axes for 24 hours each.
And finally, stage 3, the real world, vehicle testing.
Here's where it all comes together. You do the full load climb and start test, load it with 12 cubic meters of concrete, and prove it can start from a dead stop on a 30% grade.
And you test the smarts too, the active damping.
Yes, the sloshing suppression test. You induce sloshing with sharp braking, and you measure the vehicle's roll angle with external sensors to prove the algorithm is actually working and making the vehicle more stable.
And the final piece is proving the business case, right? Quantifying the regen.
Absolutely. You have to accurately measure the energy recovered during unloading cycles. That data feeds directly back into the TCO model to prove that the whole investment was worth it.
So when you put it all together, what's the core design philosophy here?
The core philosophy is the fusion of two worlds that don't often meet. It is industrial reliability designing for dust, vibration, corrosion, a 30,000-hour life, and it's married to automotive functional safety. The systematic rigor of ASIL-C, where every failure mode is anticipated and mitigated, that balance is everything.
It's incredible. Let's review the key takeaways. The huge advantage of decoupling power from the engine. The industrial robustness you see in things like the PMSM and the resolver, the intelligence of active damping, and that robust, layered ASIL-C architecture designed to prevent catastrophe.
It really is systems engineering at its most thorough, and the next step for a team that has this spec is to transition it all into a model-based systems engineering or MBSE environment.
To manage that traceability and complexity.
Exactly, to ensure that rigor stays in place all the way through production.
Which brings us to the final provocative thought we want to leave with you.
We've talked about the shift from 40% to 90% efficiency. We've talked about the high cost of robust ASIL-C compliant components. The question that ultimately defines the success of this technology is the detailed TCO analysis. How much is that efficiency gain and that massive increase in uptime really worth over 15 years when compared to the cheaper but far more costly to run hydraulic system? The long-term math has to work.
A fascinating deep dive into a system designed for a truly brutal environment. Thank you for walking us through these specifications.
It's always a pleasure to get into the details.
Until next time, keep digging deeper.